Okay, so welcome everybody to the Sustainable Places seminar. If you haven't met me, I'm TC Hales. I'm the director of the Sustainable Places Research Institute, and it's a really great pleasure for me to introduce Professor Roger Falconer to our seminar series today. For those of you who don't know Roger, I'm sure most of you do, but he is a civil engineer who has focused on water and environmental engineering problems for a long time. Most notably things like the 7 barrage, tidal lagoons, and many other projects such as that. He joined Cardiff in 1997 and has had a very distinguished career since joining Cardiff and retiring and becoming emeritus in 2018. Currently, he's a fellow of the Royal Academy of Engineering, foreign member of the Chinese Academy of Engineering, and fellow of the Learned Society of Wales. Great to have you here, Roger, and many thanks. And just to introduce your talk on global water security and integrated water management, I'll leave it to you to go forward. So thanks, Roger.
Okay, thank you very much, TC. It's a real pleasure and honor to be speaking to you today on global water security, a subject which I find myself speaking about a lot these days relative to my traditional research interests. My original interests have been involved in the modeling of hydrodynamic, water quality, and sediment transport processes in coastal, estuarine, and river basins. But more recently, I've got involved in issues relating to water security. This stems back from doing quite a lot of work in countries like India in particular. And I got involved with the Royal Academy of Engineering in 2008 in producing the document on the top left-hand page here, Global Water Security, an Engineering Perspective. And in the last 20 years, I would say, water has risen dramatically up the political agenda. And it was around about the time that this report was produced. I've taken a strong interest in this topic since and have given quite a lot of talks on it, and am now quite heavily involved in initiatives in Africa. So let me first of all highlight some of the issues. We have 1.4 billion cubic kilometers of water on the planet. That would seem plenty of water. But only 35 million cubic kilometers of that is fresh water, and we can't really do much in general with salt water. But when we look at what is actually left on the planet, we're only left with 105,000 cubic kilometers, and that's all that's accessible. A very large proportion of that 35 million cubic kilometers is locked up in ice. So we have very limited resources actually to feed a growing population, and I'll come back to that in a minute. We have the challenges of climate change. I'm not going to dwell on those today, but we are expecting the global temperature to rise between 1.5 or about 1.5 ideally, but it looks as though it's going to be more like 2 and possibly even higher than that by the end of this century. That means small mountain glaciers are going to disappear, water supplies are threatened globally, and more countries are going to face significant water stress. And when you add to that rising sea levels, then of course we have major concerns globally. So at the moment, it would appear that the global temperatures are on track to rise by something of the order of 3 degrees. Now, it isn't only climate change that's causing significant challenges to water security at the moment, but also the impacts of population growth. This was a lecture or a slide from a lecture given by Sir John Beddington, who was then the chief scientific advisor. This lecture was given in 2009. And at that time, the point was made that there would be an increase in the population from about 33%, from 6 billion to 8 billion within the next 20 years. We're well into that at the moment, and the global population is now well over 7 billion and heading rapidly towards 8 billion. So even by 2030, we will have reached 8 billion population on the planet. That means from the time when we had 6 billion, which was around 2009, and by 2030, we're going to have to produce at least 50% more food, 30% more water to meet the demands of the global population, and 50% more energy. The energy might well decline because of market forces, the percentage, but the other points have not changed much since this lecture was given in 2009. So what are some of the challenges we face? Many of our rivers are increasingly showing evidence of pollution worse than 40, 50 years ago and so forth. And in fact, some of the rivers now have poorer water quality than they would have had in, for example, Roman times. Only 63% of the world's population have access to improved sanitation. And many rivers are not only badly polluted, but they're deteriorating. The river Citarum in Indonesia is today regarded as one of the worst polluted rivers in the world, but there are many rivers across the world which are badly polluted. And when we come to water security, excuse me, 70% of the world's fresh water is devoted to agriculture. So if we're going to make any efficiencies or become more water secure as a global population, then this is the area where we need to focus. How can we make more efficient use of the water, fresh water supply that we have globally to produce more food for the future? So some of the challenges we face. 1.2 billion people today have no access to safe drinking water, and 0.5 million people, children mainly, die annually of diarrhea. Very, very, very rare that somebody dies in this country of diarrhea, but this is significant across Africa, India, and many countries across the globe. 2.5 billion people have no access to basic sanitation, and 3.5 million die annually from waterborne diseases related to the fact that they don't have access to basic sanitation. So we have contamination of groundwater, for example. Even today, women in many developing countries have to walk 5 kilometers to get 5 gallons of water or thereabouts in liters of water for the family. And this saddens me enormously to think with all the technology we've got today, with solar panels and so forth, that we can't pump water from basic channels at a relatively short distance in Africa, for example, to supply water to the door as we are used to in the UK. And flooding causes many deaths globally. And if we go back to the Aceh earthquake in 2004 in Indonesia, that generated a tsunami wave which traveled at about 500 miles an hour across the ocean. That would be about the same speed as a Boeing 747 jet. And it saddened me enormously that we were watching television programs at the time of bombs hitting garages in in Iraq with military precision. So we saw all the technology that was available then, yet we couldn't get a signal to 240,000 plus people in coastal regions when they could have quite easily moved up to higher ground, for example, Sri Lanka, and they could have avoided loss of life, significant loss of life from this earthquake and the corresponding tsunami. So about 240,000 people lost their lives in the Indo-Pacific region. And before the COVID crisis that we've seen recently, which, by the way, doesn't give you anywhere near as many deaths as the top bullet point on this page here on an annual basis. But half the world's population half the world's hospital beds are filled by people suffering from water-related diseases. So those are just some of the challenging points we see when we look at the issues of water security on a global basis. And you might think to yourself, well, that's all fine, but it doesn't really affect us in Britain. We have no effect on this particular issue. And that's something I'm going to come on to in a few minutes. So we then had the UN Sustainable Development Goals, and the aim was that these should be delivered by 2030. I have to admit that even before the COVID crisis, I was very skeptical about these goals being delivered. So let's look at some of them briefly. Access to safe and affordable drinking water for all. I doubt that many people in India and Africa are going to see that by 2030, irrespective of the pandemic. Access to adequate and equitable sanitation, hygiene for all. Again, I've got a question mark by it. Improve water quality. Well, if we just look at the UK rivers, for example, and the point is being raised continuously, the water quality is actually deteriorating. And we've seen several programs recently on television on this issue. Increase water use efficiency and address water scarcity. If anything, water scarcity is going to become more of a problem in the future. Implement integrated water resources management. I don't see a lot of evidence of that at the moment. Protect and restore water-related ecosystems. Again, I don't see a lot in that context with climate change and so forth. Expand international cooperation. Well, we've just seen the UK cut its budget to Africa, for example. And strengthen local community participation. That will, I think, definitely be delivered by 2030. But even 6.1 to 6.7, I think it's questionable whether these would have been delivered even before we face the current additional crisis with the pandemic. So I'd like to turn to the water, food, energy nexus. We know that we need water to provide energy, and we need energy to move water around our water supply system, for example, in the UK, and huge amounts of energy. The water companies are amongst the biggest energy consumers in the UK, for example. We need energy to provide food, and we need food to produce energy for ourselves, and so on. So these three are all interlinked. You change one, and it has an impact on the others. So let's look at some of the pressures on water resources. So climate change, to start with, is leading to an increasing water stress globally. The population is going to increase by about 40% to 11 billion by the end of the century. And we have the added complexity that more citizens are moving globally from the rural communities to the coastal megacities. So we're now facing an increasing challenge of a bigger variation in the population distribution across countries, including the UK. You only have to look at Cardiff Bay and see how Cardiff has increased significantly as a result of the Cardiff Bay barrage and so forth. So food production is going to need to be increased by typically 40% over the next 50 years. There's going to be new industrial demand. You can see in China, for example, when I first went to China in 1984, you hardly saw a car, it was all bicycles. And now the traffic jams in China are horrendous. And the increase in the number of cars required for China must have gone up several billion% relative to 1984. And also people are becoming richer in many countries across the world, including China, for example. They have a more disposable income, they have more goods purchased, such as cars, a change in the diet and more meat consumption. And change in diets can make a significant impact on water security. 1 kilogram of beef, for example, requires 15,000 liters of water to deliver 1 kilogram of beef, and 1 kilogram of wheat, in contrast, only requires 1,300 liters of water. So I'd like to look a little bit more closely at this issue of the water footprint and the virtual water. So we have 100% of water here that falls from the clouds. It goes through the catchment, and only about 36% of that ends up being discharged at the end of the river basin into the ocean. Obviously, it varies from one river to another, and these are just typical average values. But the point I really want to focus on here is the water comes down the river. So we have a blue river basin. Let's just take the blue water here. We then abstract that water for domestic consumption, for example. We take it out. I live in Ilkley, and the wharf is behind me. It's taken out of the wharf and it's held in a reservoir and supplied to Ilkley. But also, this water is taken out to produce commodities. And with these products, we can either use our own water to produce these products for domestic supply, or we can export the product to another country. That means we have used water in the UK, virtual water, to produce some product which we have then exported overseas. Similarly with food. We can produce food, let's say wheat. We can then use that wheat domestically, so we've used our own water for that purpose, or we can export that wheat to another country, which then means we've used our water to produce food for another country. Okay, that's fine. Now we understand the concept of virtual water. Now, if we look at the water footprint of a nation as a whole, let's take the UK, then the water footprint is the water consumed and used to produce goods and services within the nation. So the water footprint of the UK is the total amount of water that we have used as consumers, both domestically at home and in the products and food and so forth that we purchase from the stores and so on. And that consists of two components. So there's the internal water footprint. So we have crops on the land, for example, wheat in the UK. We use water to grow that wheat, and then we consume that wheat in this country. So that's the internal water footprint. We're using our own water to produce that food. But then there's the external water footprint. So we might buy wheat from another country, for example. They use their water to grow that crop, and then we purchase it. That is what we call the external water footprint. So that is the water bought in through purchase of products produced in another country. So when we look at our total water consumption, we have our water footprint of the UK. Is the water used internally? That's our own water from the rivers for washing and so forth in the home, basically consumption. But we need to add to that the virtual water. So that's the water we're importing from another country, some from products that we're buying from another country, minus exported, the water we have used from our own country to export a product to another country. When we look at the UK, and we're one of the worst in the world in terms of the volume of the external water footprint, our internal water footprint is typically 38.6 gigacubic meters per year, and our external water footprint is nearly double that. And where does that come from? It mainly comes from agriculture in other countries, growing crops and so forth, and quite a bit comes from industry, industrial development and so forth, and industrial production for commodities such as cars. So if you buy a German car, for example, that's used water mainly in Germany. So let's look at some of the values. These are figures from the University of Twente, where you have the water footprint network, which is generally regarded as one of the most reliable sources of information for the water footprint. So if I go to a coffee shop today and buy a cup of coffee, that cup of coffee is typically required 140 liters of water to produce. And the typical bath, which is often used to measure the size of the water used, is typically regarded as 150 liters. So we've used almost a bath full of water. Now, we don't produce coffee in this country. We might buy Brazilian coffee or whatever, or Kenyan coffee. Let's take Brazilian coffee. So most of the water that's used to produce the coffee that I might buy today in the local coffee shop would mainly be using coffee in Brazil to produce that cup of coffee. In the example of Brazil. Steaks, well, we rear cattle in this country, and 1 kilogram of steak would require 26 bars of water. So a significant amount of water is used in the UK domestically to rear cattle, for example, for meat consumption. But the one I really want to turn to as an example, if I may, for the rest of this talk, is cotton. So if you were to buy a pair of jeans, for example, and let's say they were cotton jeans, then they would require typically 73 bars of water. And most women's dresses would require of the order of 70 bars of water. A man's shirt would require typically 50 bars of water. These are all given and documented in detail in the University of Twente Water Footprint Network. And you can split hairs over whether it's 73 bars, 70 or 75 and so forth. But generally speaking, these figures are taken as being fairly accurate. So let's think about this a little bit more carefully. We produce no cotton in the UK directly. We import cotton within the European Union. I only have the figures here for the European Union. We've only just come out of the European Union, as you know. But we import, most of the cotton we import comes from India, for example, Uzbekistan, and so forth. Now, pretty well every cotton commodity that we buy will be based on cotton produced in India or Uzbekistan or some of the other countries here shown. Egypt, for example, is another good example. So these are all countries where we would be importing cotton from. So in other words, the shirt I've got on now is probably produced from cotton reared in India. And that means most of this shirt would have been using water in India for this shirt to have been sold in the UK. Now, we've seen in Kazakhstan, for example, Kazakhstan in particular, which used to be one of the major cotton producers in the world. The use of water and poor water management to produce large quantities of cotton for the rest of Europe in particular has led to the Aral Sea basically disappearing. So now that sea doesn't really exist in any significant way. They are trying to generate this sea, but by and large, it's not making much progress. And we see here that we can no longer turn to industries that would have been very viable about 40 years ago in the Aral Sea, such as fishing. We looked at Lake Chad, for example, in Africa. That has decreased dramatically in the last 40, 50 years due to overgrazing, desertification, devastating impacts on water supply for 30 million people in the region. So if you look, our culture has a significant effect on this issue. Let's take these two news presenters in this picture. The man could wear the same suit every day of the week. He could wear a white shirt every day of the week, and he could wear the same mauve tie. Nobody would comment on it. Barack Obama, pretty well every picture you see of Barack Obama when he was president would be with him with a gray suit on, a white shirt, and a mauve tie. In contrast, if the woman newsreader were to wear the same dress every day of the week, people would be asking questions, criticizing her dress and appearance and so forth. And I ask myself, why? And we know that that cotton dress will require a huge amount of water in a country like India, for example, to produce. So by the very culture in the West, we are using huge amounts of water in countries to rear cotton to meet Western cultural demands. Not just the West, the same would apply in Australia, for example, and increasingly in countries like China. So the male newsreader can wear the same suit daily and the same colored shirt, for example, and no comment would be made, but the newspapers, many of the newspapers will be focusing on the appearance or the dress and so forth that the woman is wearing. We have spent, my next point is, we have spent significant amounts of money on developing the motor car, for example, and you only have to look at the amount of money that goes into Formula One, which is huge. And the efficiencies of the car engine have improved dramatically over the last 20 or 30 years as a result of these investments. I know that if you look at something like, well, just take the Formula One. I know that in about 2010, they were all told that they had to complete a race when they switched from refueling during the race. They had to complete the race with only about 150 kilograms of fuel. If I can't remember the figure, I think it was 150 kilograms of fuel. And all the drivers said, oh, that there's no way we can do that. Anyway, they had to manage the cars and the race better than before, and there was not one single driver who failed to complete a race due to lack of fuel. Then a few years later, it was reduced from 150 kilograms to 100 kilograms. And again, the drivers were all complaining right, left, and center and saying that this was not possible. Every driver was going to be out of fuel by the end of the race. Well, again, we've not seen it. And that has been reflected in domestic cars as well. My wife has had a Volkswagen Golf, and we've replaced it every 3 or 4 years or whatever. And each time, it's a lot more efficient on petrol consumption. However, when you turn to water, which we can survive without the motor car on this planet. We've done so very successfully for umpteen thousand years, but we've never survived without water. And when you look at the investment that's gone into irrigation, for example, by comparison, it is really small. We haven't made these dramatic improvements in irrigation that we see in the motor car. And 70% of our water is used for agriculture. So it doesn't seem logical to me that we spend so much on developing the motor car, and yet we spend very little in refining irrigation to produce much more crop per drop. And who pays for the water? When we pay for our water bills, we are actually only paying for consumptive use. In other words, the water company to supply water to me at my home, and then to take it away and clean it up and put it back in the river. But what happens to the shirt that I've got on right now, for example, which has been produced probably in India? Who is paying to treat the water in India after the cotton has been fertilized and so forth and polluted? Probably no one. So if you look at the price of water we're paying here for consumptive use, it's probably these figures below are even lower, should be higher now than they've shown here. But you can see that if 1 pint of beer is costing you more than 1 cubic meter of water per week, and 1 cubic meter of water per week is about the daily consumption of the typical British citizen. And who's paying for ecosystem services? Who pays to clean the rivers up? Who pays to maintain the ecology of the river? Virtual water costs are needed to be included in crop production, not just in the UK, but also in countries like India, for example. And if you look at the polluted wastewater, this is a picture from the Why Not Cotton fraternity. You can see the pollution in the river here from the dyes and so forth that are used in these countries. So I would leave you with one thought here, that I would be quite happy to pay more for my shirt. This shirt I've got on from a major UK store probably cost 20, 25 pounds. I would be happy to pay another 25% on that to ensure that the company that was buying the cotton was insisting and guaranteeing me that the water was treated before it was put back into the river in that country. And then I don't mind how many dresses a woman would want to wear to read the news every day and so forth. But at the moment, that's not happening. And things are getting worse in many of these countries. So the cotton wastewater discharge in the rivers often contains very high levels of pollution, fertilizers, and children are dying as a result of this in many countries in the world. And then we see vertical farming as a good example. I think vertical farming offers considerable opportunities to dramatically reduce the amount of water that's needed to produce food for us. So here we could see significant advances in farming, but it's not moving at anywhere near the pace that the Formula One car, for example, and consequently the knock-on effect on the domestic car. But here, this is not the best of pictures, but there are pictures of vertical farms where you have almost operating theatre standards. Everything is maintained by computer and totally controlled. So you have no fertilizers, you can control the sunlight intensity, you can grow the crops under controlled conditions, you can produce organic quality crops with only 1% of the water needed for land production. And yet I don't see this exploding all over the world. And it seems to me that this is something which we should be really investing in rather than refining the efficiency of a car engine. And then I'd like to turn to some other points about the way we've designed things historically. So even in Cardiff, for example, we take the water in from the river, from the reservoirs, the Brecon Beacons. We then distribute that water and pump it all around the city. And then we discharge back into the sea. Now, you've got low environmental flows because you're taking out so much water for this growing city of Cardiff. We've got low environmental flows in this reach, in the summer months in particular, when everybody's having a shower every day and so forth. And that is having a huge knock-on effect on the ecological characteristics and maintenance of good ecological, high ecological status in the river. And it would be far better if we were to take the water in at point A, distribute it around the city, and then put it back in almost at the same point. Now, we built the Cardiff Bay Barrage, and that actually gives us an excellent opportunity to do this because we've converted what was once a saltwater bay, Cardiff Bay, into now a freshwater lake, effectively, and right on the doorstep of the city of Cardiff. So this concept of taking the water in from the end of the river basin, i.e. in Cardiff Bay, taking it through a treatment works and then distributing it all around the city and then sending it back into Cardiff Bay, treated to the same standard as the intake, is the long-term solution which could offer us much better ecological status in many of our rivers, for example. And particularly since we are looking at megacities developing more and more rapidly around the world. And now I want to turn to the cloud to coast concept. So the rain drops from the clouds, it comes into the catchment, and we can model the catchment, we can model the sewer, we can model the groundwater and so forth, and then we can design our system accordingly. But it's not very well designed at the moment, in most cases, including the UK. The problem is, you look at a major company, for example, that's responsible for the design of the system, you'll have people who are experts in hydrology. They don't really talk to people who are experts in hydrology or sediment transport processes. You have groundwater modelers, you have river modelers, modelers, you have estuary modelers, you have 3D coastal modelers, and they very often don't talk to one another. Or if they do, it's only on peripheral issues. And even the modelers who are trained in civil engineering and water engineering don't really understand much about the biology. They'll spend a lot of time focusing on the roughness on the bed and how that impacts the flow. But then when it comes to putting in the biological decay rate for E. coli or fecal indicator bacteria, they will just use a constant value day, night, and whatever the temperature and whatever the sunlight intensity and so forth. And they won't worry about the accuracy of that. So we have to work towards a system whereby we look at the system as a whole, and we look at the whole catchment and don't just pick up the bits and pieces or develop good ecological status in one part of the river. And we see this at the moment with a lot of publicity around the town I live in, Ilkley, where the Ilkley Clean River Group has managed to get the town of Ilkley focused as a bathing water stretch of river. It's the first and the only one in the UK. So I'm now going to turn to two particular examples of why it's necessary to look at the system as a whole and not just take part of the system out. And over 150 years ago, this country built many weirs and rivers, mainly for energy production, but mainly to manage floods. And what happened there, we would have flooding in a particular community, let's say Ilkley, where I live, it floods regularly. You'd build weirs to manage the water, basically do the same as people are now wishing to do with natural flood management, which is hold the water back at the upper catchment, although here we're just holding it back further up the river. You then make the flooding worse further upstream in the river, not so much in the upper reaches of the catchment. So now, when people look at moving these weirs, which many would wish to do, you're putting the river back to the natural system before the weirs were ever built in the first place, and reintroducing flooding in many cases to communities where they didn't have flooding before. So if we look at Ilkley, where I live, for example, we have pristine river conditions about 5 kilometers just upstream of where I live here. We often see cattle in the river, and those cattle are leaving waste either directly in the river or very nearby. There's no fencing off of the river. So that's diffuse source pollution. We also have very mountainous terrain around here, although you can't see that from this picture. And when we have high flows, the sewer can't cope with it, and we get combined sewer overflows with pollution coming directly into the river. And just downstream here, we see a large number of bathers in the local community. A citizen science program has been developed, and you can see here large numbers of, very high numbers of fecal coliform here from E. coli, from the sewage treatment works under low flow conditions in July and then high flow conditions in winter, and well in exceedance of the bathing water standards during the summer months. You have to question some of this data because this drops from 35,000 down to 10,000 in low flows, and yet it drops from 39,000 down to 5,000 under high flows. Anyway, that's an ongoing project at the moment. And he makes the point that not only is water quality of concern globally in countries like India, for example, and major parts of Africa, but also even in the UK now, we are seeing E. coli levels in rivers which are of growing concern in the UK. There was a panorama program on a few weeks ago. So I'd like to turn to an example which I worked on pretty well the whole of my time at Cardiff University, and this was the non-compliance of the bathing waters in the Blackpool region in the northwest of England, and the concerns about this and how it needed to be addressed. So the compliance point is in the region of Lytham St Anne's, and at this point, designated by the Environment Agency back in the early 90s, it had to meet the EU 76 standards originally, and then the latest bathing water directive from the Water Framework Directive. And Blackpool is still, even with this picture was taken in 2018 before the pandemic. I suspect it's going to be even more crowded this year. But in 2018, without the pandemic, you can see how crowded it was in the summer months. And there's a lot of people bathing in the bathing waters. If you go back 1965, you can see it was crowded a lot more, and people didn't travel there to places like Spain or Portugal and so forth for summer holidays. So, big concern, major UK British seaside resort failing to meet the 1976 Bathing Water Directive in the early 1990s. So storm sewers and sewage works discharging along the coast were thought to be the main problem. They didn't even include the river in the modeling studies at the time, and they designed a long sea outfall, and that discharges into Loon Deep. Field surveys were undertaken, a lot of money was spent on field surveys, but it didn't really solve the problem. And they found after they'd spent a lot of money on this long sea outfall, they still had challenges of bathing water quality at the compliance point. United Utilities invested 500 million in the period 1993 to 96. They built 3 new wastewater treatment works, 5 new pumping stations, and so forth. Much of this investment probably needed to be undertaken anyway, but it didn't solve the fundamental problem. So we got involved back just before I came to Cardiff, but the work was mainly done at Cardiff. We then advised them that they really needed to model the river. They needed to model up to the tidal limit. Excuse me. And I thought at that time that would solve the problem. It did help in many respects. First of all, we needed to check our model. We had good hydrodynamic data. The red dots are measured data, excuse me, and the blue line shows the predicted data from the model. And you can see here there are good comparisons. Now, if you're a modeler and you're wanting a grant income from EPSRC or NERC, you don't really want good agreement. You do if you're a consultant, but you don't if you're an academic, because you want to be able to say, my model is not giving good data, good predictions. I need to spend more money on it and do more research and so forth. So not ideal. But then when we modeled fecal bacteria, fecal coliforms in this case, we found the model gave very good predictions. And fecal bacteria can vary dramatically. You can take 2 samples either side of a canoe and you get very different values. But again, we were getting very good predictions here. And in 1999, we found that under dry weather conditions, we had very low levels. This is in the river, this is in the estuary. It's at a site called Lembile Post. This is before you get to the compliance point. And you can see here that you have very low levels in the dry conditions, no rainfall in the preceding days. And generally speaking, it's at 1,000 or well below. Under wet weather conditions, when it's been raining the preceding day or two, you can see it's up to 50,000 fecal coliform units per 100 mil. And then if we do some simulations, we see here, black is the compliance point, yellow is significant failure. And you can see that under the wet weather conditions, the problem is not discharges from the coast, but it's from the river. So we then focused a lot on Preston, which was just upstream, excuse me, of the tidal limit. And we took the model a bit further up, but that still didn't prove the point. So we then needed to go much further upstream, right up to the top of the catchments, and model the whole system. And we did this through a large NERC project called Cloud to Coast. We modeled from right out in the open sea. We took data here from our Irish Sea model. We modeled all the catchments. That was mainly done by Sheffield University. This was a partnership between Cardiff, Aberystwyth, and Sheffield University. And here we were looking at E. coli, and we were including sediment transport processes in the modeling. This was the first time that anybody had looked at sediment, well, first as far as I'm aware, that we had looked at sediment transport processes in affecting fecal bacteria from the catchments right down to the coast. And I must admit, I felt when we started this study that this was just going to be a red herring and a bit of a waste of resources looking at the sediment transport processes in terms of fecal advection. We also looked at climate change and land use changes. So there were 28 catchments in the region. They're all shown here. This is Lytham St. Anne's, and this is the bay that was covered. And there were very many rural catchments, mainly farmland, and there were urban catchments such as Preston, for example. There were steep catchments, mild terrain slopes, and various land use types, arable farming, and forested and so forth. So we pretty well had everything in this mix. We had cattle waste, E. coli, on the land in the upper catchments, the farmer spreading it from the cowsheds over the fields, so fairly uniform distribution over the land. And we had cattle directly in the river and doing what they do in the river. All this was then traveling right down to the estuary and along the Faecal coast. We also had septic tanks, of course, which had to be cleared, and some of that was leaking into the groundwater. So Aberystwyth University, David Kay in particular, and his team took measurements in the catchments of pretty well everything. There was a very major field study in the rivers, in the coasts and the estuaries, and in the wastewater treatment works. So wastewater treatment works was done by Sheffield University. And we did all the modeling. We wrote our own new 1D river model, and we developed our own catchment model. We were using the Stanford HSPF model, but we found our own model developed at Cardiff was in fact better. And here we can see that by and large, the model is predicting the measured values and the predicted values pretty accurately for E. coli. There are some outliers, such as here. But when you think of how variable, you look at the cowpack, for example, and the rainfall intensity, it's very difficult to know exactly what the source is at a particular point and how it varies. It's very episodic in many cases. And then when you come to bacteria, what happens here is the bacteria is in the water column. You have your sediment particle. The bacteria is absorbed onto the sediment particle. The sediment particle is now in suspension and it drops down to the riverbed. So your bacteria is in the dissolved form in the river. Some of it goes to the sediments. The sediment and it decays. Some of it decays. Some of it goes onto the sediment particles, and after the storm recedes, it goes onto the bed. In the bed, it hardly decays. And then the next time the storm comes, that sediment is picked up from the bed and desorbs bacteria into the water column. So you have a very complex interaction between bacteria and sediments on the bed, and then sediments in suspension. Well, I was very surprised at the levels in the sediment. If you actually look at the FIO indicators, fecal bacteria indicators here, we find that in the channel, the suspended sediments are of the order of 0.6 times 10 to the 16. In the, that's the blue, the water in the channel. If we look at the suspended, the sediments on the bed, we've got even higher values in many cases. The green line is generally higher here. So the concentrations in the bed before the storm picks up, or those that haven't been picked up yet, is very high. And then we have the sediments in the water column, and that's the red here. So the conclusion from this study is not only do you need to model right from the upper reaches of the catchment right down to the end of the river if you're going to really model fecal bacteria, but also you have to include sediment transport, because sediment transport can be a major process in terms of modeling and predicting fecal bacteria levels at the end of the river basin. And another point, people tend to take bacteria levels in the water column and average them and use depth average values. However, in a more recent study in Swansea Bay, we found that the value varies dramatically from the surface. This is the decay rate to near the bed, because near the surface, there's a lot more light penetration and the bacteria decays very quickly. So here on the left, we're using an average value over the depth, and you can see we're predicting pretty high levels. On the right, we've got exactly the same criteria, except now we're using the formulation which we've refined ourselves as well, to show that the bacteria level decays much more rapidly on the surface than near the bed. In other words, if you use a 2D model or a depth average model, which is what's being used in most studies across the UK at the moment, you are over-predicting the fecal bacteria levels in the surface levels because it's decaying much more rapidly through the light penetration. In contrast, the fecal bacteria levels near the bed are much higher than you predicted. And that's the part of the food chain where your shellfish exist, for example. So we are under-predicting the concentrations on the bed, in the shellfish, in the food chain, but over-predicting in the surface layers. So again, this is a complex three-dimensional process. So my conclusions: climate change is increasing the impact on water security, and it needs integrated global solutions, and we see that. Virtual water needs to be better understood by the public, political leaders, industry, and so forth. How many people realize that every time they buy a shirt or a dress in a shop, that they're actually having a huge impact on water resources in a country like India, Egypt, Africa, and so forth? And I don't know about you, but I would prefer to pay a bit more and buy clothes if I knew I could be guaranteed that the water was treated before it went back into the river, affecting the health of young, vulnerable children in those countries. Water security needs integrated management approach. We can't just take out an isolated town or community and solve the problem for that community without looking at the knock-on effect in the whole system. Hydro-epidemiological modeling is extremely complex. So we need not just mathematical modelers trained in engineering departments or mathematics departments, but we need to work as a big and strong team, bringing biologists, chemists, and so forth, all to the table, all to these models. And finally, sediment transport when we go to an integrated approach, we see that sediment transport is a very major transport mechanism for bacteria in rivers.
Well, thanks all. First of all, Roger, it was really interesting and comprehensive, as we would expect. So we've, if I could ask everybody to start, if there are any questions, to start putting them into the chat, and I will moderate those as we go through. We've had a couple in already. The first one's from John, and his question is, should we be looking to use other crops such as hemp to provide fibers for cloth and clothing?
I don't know what, in principle, yes, we should look at all options. I don't know how much water hemp requires compared to cotton. I guess John knows a lot more than I do about that. And I guess by his question, he's assuming that we're assuming that hemp would require far less water. If it does, fine.
Yeah, great. So another question here from Paul. So I guess this must be in reference to the pollution element of your talk, but couldn't physical chemistry and chemical engineering give answers to many of these questions around pollution? And what are your thoughts on that?
Well, we need the strongest, largest team that we can bring together to solve some of the major problems. But I don't think chemistry alone will solve many of those problems. We need to make sure that we reduce the amount of water that's used to grow the crops in the first place, for cotton, for example. We need to make sure that the water is treated, in my view, before it goes back into the river, whether that's in the UK or whether it's in India or Egypt or Africa. And chemistry will help, but it won't solve all the problems. And sometimes you use chemical processes which solve one problem and create another. Chlorine is an example.
Brilliant, thanks. So there's more coming in here. So Herbert has a question. Is there a contribution small community groups can make to taking measurements in local water courses? If so, with what equipment?
Yes, we have quite a lot of that at the moment in Ilkley with the Citizen Science Programme, which is where the data is reported on the television quite frequently. You've probably seen it. The Ilkley Clean River Group has had a lot of publicity in recent months. The problem is it's often taken at spot sites down the river, different times and so forth. And I'm not saying that that's the case with the Ilkley Clean River Group. I currently chair the Wharf Partnership Board, which deals with the bigger picture of the wharf, and it's a consortium of major companies. But it's a very good example of where I think engagement of the community is a good thing. But we also need more controlled or more involvement with the companies so that we are collecting it on a traditional academic basis, if you like. The work needs to be done that if it was peer reviewed for a journal, even though it may not be novel, but it would stand up to the rigor of academic credibility. I'm not saying that the data for the Ilkley Clean River Group doesn't meet those criteria. We have a fellow of the Royal Society, Rick Batterby, leading that work. But in general, it's not just a matter of people going out and taking measurements and then telling us it's going to solve the problem. I can think of many examples in flooding where I've done a lot of work over 40 years where sometimes the locals have gone out and collected something and tell you without any understanding of fluid mechanics, hydrology, hydraulics, whatever word you want to use, and come up with a solution which you know full well is not going to solve that particular problem.
Brilliant, thanks. So another one here from Sam. If we reset the Sustainable Development Goals, what are the timescales for SDG 6? Is it a case of now or never?
Well, I wouldn't say never, but I think it's a bit like the pandemic. The pandemic solved pretty rapidly in the UK, or appearing to be solved pretty rapidly, but it'll take years probably before it's solved in Africa. So I think it's the same with water quality in rivers. I think people will still buy. Well, I'm not sure, actually. I was going to say people will still buy clothes and they couldn't care less about water pollution in other countries with the virtual water point. But I think if you get more, if people become more educated and we focus much more on the impact of changing address every day of the week, for example, to read the news, that is having an effect on water quality in countries like India. I've seen it a lot in India. Sorry to keep referring to India, but you just see it. There's dramatic differences. Then I think people will change. I mean, I noticed this about the time that I came to Cardiff. There was a big fuss about people working on the coffee plantations and paid very, very little. And then I think it was Starbucks. I don't remember if it was Starbucks, but one of the main stores introduced the fair trade coffee principle, and that they would only sell coffee provided that the people were paid a good wage. And there'd been quite a lot of adverse publicity in the news. And I was amazed how many people suddenly said, no, I'm not going to buy coffee from the shop. I'm going to buy it from Costa or Safeways or Starbucks and so forth, and pay a lot more because coffee prices went up dramatically. You could buy coffee for about £1.50 or £1 at the time or whatever it was. And all of a sudden, if you went to the stores where they were advertising and promoting fair trade coffee, it was almost double the price. And yet those are the stores that have thrived today and so forth. So I think if companies were told to make sure that the water was treated before it went back in the river for producing cotton, hemp or whatever, then I think people will in due course pay more and be prepared to pay more.
Brilliant. So John has provided us with a couple of links to comparisons of hemp versus cotton. So thank you for that, John. So another one here from Alex. You mentioned that you'd be happy paying more for clothing made by companies that guarantee water treatment in the country of origin, but who would enforce that effectively? What would that country's government enforce those standards, or would it be the job of the country importing the clothing?
Well, I think it would be like the fair trade coffee issue. I mean, some countries have claimed fair trade coffee, and the UN in particular has flagged up those countries and said, well, this is not the case in those countries. And I'm not quite sure how the fair trade coffee concept works, but I think that mainly operates through the UN. I stand to be corrected, but I don't see why a similar principle couldn't be applied in other countries. We would see it because if the number of children dying in certain countries because of gross pollution in particular rivers wasn't improving as a result of reduce. You could see in the picture I showed you. It's one of the worst pictures I've ever seen, obviously. But the green water, if that isn't improving, then we have to ask some questions. I don't quite know who would implement it, but it seems to be quite effective with the fair trade coffee.
Great. I have a quick question, hopefully.
Sure.
So I found the bathwater analogy really helpful and useful. But one thing that I got sort of question is that, coffee only grows in tropical locations that have plenty of rainfall, whereas cotton is obviously grown in water poor areas. And I'm just wondering how effective that might be. It's good at the macro scale, but how there might be a way to impart on people the importance of the baseline water conditions when sort of describing that going forward.
It is an oversimplification of the problem, I accept that, but it's a message that's quite powerful in my experience. The problem is in the UK, and what I found when we were dealing with when I was involved in the Royal Academy of Engineering report back in about 2008, the debate tended to be, well, a cotton shirt would require so many litres of water, not put in the context of a bathtub. but it would be, let's say for the sake of argument, 150 times 50. Somebody else would jump up and say, no, 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 I'm an academic at a prestigious university and it doesn't require, let's say 50,000. Just pull a figure out of thin air. It only requires 45,000. And then somebody else would get up and say, well, no, I'm sorry, I'm an academic from a very prestigious university as well, and it requires 55,000. The politician sitting in the audience, and I watched it with sadness, would turn around and say, well, you academics can't sort this out, so I'm going to walk away and forget about it. And that was a real problem because we were splitting hairs over whether a shirt required 50,000 litres, 55,000 litres, or 45,000. That plays straight into the hands of the politician who want to kick the problem into the long grass. I think when you talk in terms of bars of water, and also 50,000 litres doesn't mean anything to, politicians go on television every day and talk about figures. So we're putting 6 billion into this, that, and the other. People don't understand that. So I think linking it to a bath of water helps, although it does, I accept, somewhat oversimplify the problem.
Yeah, brilliant.
It also helps, on one other point, if I may, it helps us focus on using water in certain countries to produce products rather than countries where it's not really suitable for producing products. We can see in the UK at the moment, we're wanting to shift to wine production as a result of Brexit, because it's anticipated the wine is going to go up for us in the UK, for example. And is this the right country to produce wine? I don't know. Although, having said that, I like the English wine at the moment.
I appreciate that we've taken up a lot of your time. There's a few more questions have come in. I'm going to leave you with one more, if that's okay. And then if I'll ask everybody else to maybe email you or get in touch elsewhere. So this is from a former student of mine, former undergraduate of mine, Sia. How could we ensure that companies are indeed ensuring they're utilizing water responsibly, i.e. remediating the water they are polluting? For example, hasn't it recently been revealed that sustainably sourced palm oil or sustainable fishing aren't necessarily truthful? Truthful.
Absolutely. I totally agree with that. But one of the things I did find encouraging, I chaired yesterday a major international event with about 5,000 people involved, and it was on a series of events I'm leading at the moment on global water security through the International Association for Hydraulic Research. And yesterday, the focus of the 3-hour event was 3 speakers, all on policy. And it was led by a woman called Kate Lamb. She was the first speaker and the keynote speaker from CDP. And CDP is dealing now with companies where they're talking in terms of investments of trillions of dollars. And they're sending out water questionnaires, focusing companies now, and water's gone right up to the board level in companies as to how they can minimize and optimize their water use. These are big companies, Ford. She went through a long list of companies and so forth. So I do think things are moving, and through companies, huge global NGOs like CDP, and I encourage anyone to go to their website if they're interested. And her name was Kate Lamb. She's the head of global water security for CDP. And she gave a very impressive presentation yesterday on this very point. And I think things are changing slowly. At the moment, the focus is on climate change. But I think water is just as important as climate change. I used to tell my first year students who used to do fluid mechanics with me, this is a very important course for you. We've lived on this planet without the aeroplane. We don't need aeronautical engineers. We've lived on the planet without lights. We can cope without electrical engineers. We've lived on the planet without the motor car. We don't need mechanical engineers. We've never survived without water. So you need water engineers and scientists.
And scientists. I think that's an excellent point to finish. So thanks, Roger. For those of you that still have further questions, I'm sure Roger will be happy to take any further questions via email or any other way like that. And just to say thanks again to you, Roger, and thanks again to everybody for showing up. And we have 2 more seminars in this series, so I look forward to seeing you in the next few weeks. So many thanks to everybody, and have a good rest of the day.
Thank you.
Cheers.
Bye.